we can go ahead and get started talking about related rates. So there's two big sections in calculus that are word problem sections. Related rates is the first big word problem section, and the next big word problem section is optimization, which we get into pretty soon in Unit 3, I believe. So this section is word problems. It is purely word problems. That is all related rates are. They are word problems. And I know for some people that's a disappointing thing to hear. I know that a lot of people don't love word problems, but now is the time to try to embrace word problems. I'm going to try to make it as algorithmic as possible. However, word problems are never going to be an algorithm. It's never going to be like differentiation where you know what to do all the time, or you can always know the right path to go down. With related rates, you might try something and it might not work out at all. I mean, here I am. I have a master's degree and a bachelor's degree, both in mathematics. I've been teaching mathematics for, I think, 7 years now. And I still sometimes see these problems and I go down the completely wrong path. I'm a lot better at it, right? I can make the good choice most of the time. But there's plenty of related rates problems where I start it and I'm like, yeah, this isn't working. And I have to restart. And that's just a normal process of word problems. And I want you to know that. So as you're practicing them, you're not getting super frustrated. So I will give you a process, though, that makes it a little bit easier. And I'll try to make it as pain-free as possible. Ugh, sorry, let me just adjust myself a little bit. All right. So, and I'm going to move some stuff around. There we go. In terms of related rates, it's about rates that are related, believe it or not. So, as our motivation, we have a perfectly spherical snowball rolling down a hill. I'm an artist, of course. I'm sure all of you know how much of a beautiful artist I am. Beautiful. It's a snowball. It's rolling down the hill. And we know how snowballs work, right? Or in theory, how snowballs work. You roll them and the snowball gets bigger, right? So this snowball right here, it has a volume. And as it rolls down the hill, it increases over time. So we can say that the volume of the snowball is a function of time. And we also know that if its volume is increasing, its radius is increasing. The radius of this snowball is increasing. So the radius is increasing over time. So there's a few things here. Volume is a function of time because it changes as time goes forward. Radius is a function of time, the radius of the snowball, because as time goes on, the radius gets bigger. It's a function of time. That says time. Just use your imagination. But we also have that the volume of a sphere is related to the radius. So the volume of a sphere is related to the radius, and both the volume and the radius are functions of time. We can relate the two together using the relationship that volume, here's the volume of a sphere right here. The relationship the volume of a sphere has, if we know information about how the volume is increasing or how the radius is increasing, we can relate those things together to find out information about one another. So really, related rates is about finding how two rates are related and finding out something about one of the rates you don't know. Maybe you don't know how the volume is increasing, but you do know how the radius is increasing. If you know how the radius of the snowball is increasing, you can use that information to find out about how the volume is increasing. So I'm going to talk about the general procedure, and it's not going to be super useful until we actually use it. But this is our motivation, just kind of talking about how rates are related to one another. So here's the idea. There's going to be a word problem. Read the problem carefully. That's your first step. Take your time, digest all the important details. With word problems, you can't skip over the word part. The word part is important. This step says, just read it, okay? I cannot tell you how many times I've had a student come to me and be like, I don't know how to do this problem. And I say, oh, okay. So what is the problem asking for? And they're like, I don't know. Okay. You have to read the problem first. Giving up when you see a chunk of words before you've even tried to parse through it is a one-step plan for failure. If you give up without trying, without reading, without believing that you can do it, you're not going to get through any of these problems. You're going to have to be uncomfortable, and that means reading through it again, maybe reading through it a third time, and getting all the information possible, and then just grappling with it. So please read the problems. It's important, it's necessary. First step, after you've read the problem, draw a picture. If possible. Not all the problems have pictures you can draw, but if possible, draw yourself a picture. You'd be surprised at how helpful those pictures can be. You don't have to be an artist. I'm not an artist, all right? You just have to be able to draw diagrams. Making a diagram, even if you find out that your diagram is wrong, starting by drawing a diagram helps a lot. Just read what you have and then try to draw a diagram of what's happening. For instance, when I was like, a snowball starts rolling down a hill. All right, what did I do? Okay, I know what a hill looks like, right? All right, here we go. Hill. I know what a snowball looks like. It's a circle. Circle. Will this picture be helpful in the problem if there was a problem here? Who knows? But I can draw that diagram, right? I'm using the basic English that I know to draw that diagram. All right, then comes the important part. You gotta write down what you know and what you want to know. So I'll show you this when we get to it, but it's important to identify from the problem what you know and what the problem is asking for. Between what you know and what you want, you should have at least one formula to work with that involves the desired quantity/rate. So this what you want part, you're going to want a formula that relates what you know and what you want. Then we do some differentiation. Then we solve for the desired rate. Then we reflect on the problem. So I'm going to show you how this process looks. Here's some useful formulas. These are just formulas that get used in related rates a lot. Pythagorean theorem, you're going to see a lot. Circles. Here's the area of a triangle. Here's a different area of a triangle. Here's the area of a trapezoid. Surface areas, volumes. All of these happen. You see all of these formulas get used in related rates problems. For all the problems in related rates, for your homework, for the exams, for the exam review, you want to round your answers to 2 decimal places if necessary. So like if your answer doesn't have any decimal places, that's fine. But if it does have decimal places, round to 2 and then include units. So let's get started. Let's go back to that idea of a snowball. So my first step here, reading the problem. Suppose a snowball is rolled down a hill and is coming toward you. As the snowball rolls downhill, the radius is increasing at a rate of 0.45 inches per second. Determine the rate of change of the volume of the snowball when the radius reaches 14 inches. So I've read the problem. My first step, step 1, I'm going to draw a picture. Will it help? I don't know, but I'm going to draw a picture. All right, so there's a snowball. It rolls down the hill, and it says it's rolling towards me, so I don't know if that's going to be important. It doesn't matter, but I'm going to draw me right down here. Oftentimes at this point, it's useful to see if there's any geometry in the problem. Some problems won't use the geometry of the picture, but a lot of them will. So if I'm looking and wondering, maybe is there some geometry here that could potentially be useful to me later, I would say, well, maybe if I need to, not sure if I do, but I could say there's a right triangle here. Not sure if that'll be useful, but we could say there's a right triangle. Is there any other information they gave us I can use? We roll down a hill. It's coming towards me. It rolls down, increasing at a rate of 0.45 inches per second. I'll come back to that information. Determine the rate of change of the volume of the snowball when the radius reaches 14 inches. Okay, well, that's about enough information. That's all I can do for a picture. So our second step, we want to identify what we know and what we want to know. I like to kind of just make two columns. I picked this up from my undergrad calculus teacher. And I think it's the most genius it's the most genius way to organize the information you have. Typically the information you're given is the numbers. There's like numbers in this original thing. So I'm just going to kind of look at the numbers. So we have radius is increasing at a rate of 0.45 inches per second. And then it specifically asks me to determine the rate of change of the volume of the snowball when the radius reaches 14 inches. So in terms of what we know, the only thing that we know for a fact is that the radius is increasing at a rate of 0.45 inches per second. If the radius is increasing, let me talk about dr dt. This is the derivative of the radius function with respect to time. So how is the radius changing with respect to time? So here, when I say what I know that the radius is changing. DRTT is how the radius is changing over time. It's increasing, so this should be positive, at a rate of 0.45 inches per second. This is what I know. It's the only thing I really know in terms of numbers. I am being asked to find the rate of change of the volume of the snowball when the radius reaches 14 inches. So the rate of change of the volume, that would be dV dt. That's how the volume is changing over time. So we want dV dt, and we want it at a particular time. We want it when the radius is 14 inches. So radius I'm going to call r. So when the radius is 14 inches. When you identify what you know and what you want to know, you need to have a way to relate the two together. So we need to be able to relate together radius and volume. So we need a formula that does that. Right? Radius and volume of a sphere. That's important because it's a spherical snowball. So the formula that relates the volume of a sphere and the radius of a sphere is V equals 4/3 pi r cubed. This is the volume of a sphere formula. Four-thirds pi r cubed. Step 3, you're differentiating with respect to time. and time is t. So what we're doing here is just like we did with implicit differentiation when we took a derivative of y. When we took a derivative of y, we had to put a dy dt in. We're now pretending that volume and radius are functions of time. And we're going to treat them like we treated y's when we were doing implicit differentiation. So let me make a note of that right here. So the derivative of v would be dv dt. Instead of dy dx, we'd use dv dt. The derivative of the radius would be dr dt. So I'm going to start by writing my formula down. V equals 4/3 pi r cubed. And then I'm going to differentiate both sides of the equation with respect to t. So I'm going to take the derivative. D dt is an operator. It says take the derivative. And maybe I'll note that here. So d dt of something means take the derivative with respect to time of the whatever's inside here. Whatever's in the inside. So the derivative of volume would be dv dt. And then over here, there's no product rule or anything because pi is just a number, 4/3 is just a number, so we just have to treat r cubed like it were a y, right? So this 4/3 pi I'm going to leave alone for a second. Then the derivative of r cubed would be 3r squared, and then a dr dt, because we're using chain rule here. And we can simplify that a little bit because these 3's would cancel. And we get dv dt equals 4 pi r squared dr dt. Step 4 is plugging in the values you know. And then solving for the ones you want. I want to make a point right here that even though I know that I want this volume, this dv/dt when the radius is 14, you do not plug in the radius until you finish taking derivatives, because this radius is only going to be 14 inches at one moment in time. Taking the derivative and plugging in this radius would mean that that radius stays 14 inches the entire time the snowball is moving, and that won't work. So it's important that you don't plug in any of these numbers that you have until you're done taking the derivative. So the values that we do have, we know that dr dt is 0.45, and it's inches. You can put the inches in, but we're just going to put the units at the end at this point. And we know that the radius is 14 inches. So plugging those values in, dv dt is equal to 4 pi, and then here we have r, right? So 14 squared times dr dt times 0.45. And if you plug this into your calculator, you should get, it's approximate because you have to round it, you should get 1,108.35. And then in terms of what this rate is going to be, I'll show you how to do it by plugging in, but normally what I do is I just say, okay, it's a rate, so it's going to be per a time unit, and the time unit we've been given was seconds. And then volume is measured in cubic units. So this would be inches cubed per second because volume is measured in cubic units. Now what you could do with those units if you wanted to, instead you could say that dr dt is 0.45 inches per second and that the radius was 14 inches. And you could plug it into your dv dt. So you have 4 pi, and then instead of 14 squared, you do 14 inches squared. And multiply by 0.45 inches per second. This square would get distributed to the inches, and it would also get distributed to the 14. So you'd end up with this 1108.35, and then you'd have an inches squared times in inches per second, and then inches squared times inches per second would be inches cubed per second. So if you really wanted to go that route, you can figure it out by actually inserting the units in there. But it's kind of easier at the very end to just note what the units are and what it should be if it's a derivative and just answering it that way. But either way works. Questions on that first example? We will be doing more examples, of course. All right. So, example 2.7.2, an 18-foot ladder is leaning against a building. The ladder starts to slip away from the wall at a rate of 0.75 feet per second. How fast is the ladder sliding down the building when the base of the ladder is 7 feet away from the wall? Now, this really should say that the base of the ladder is slipping away from the wall. Ladder problems are a staple of related rates. So our first step is drawing a picture of this. So I'm going to draw a wall, and we have an 18-foot ladder leaning against a building. And I guess this is the building. That's my building. Here's a wall, and then this guy right here will be my ladder. The dimensions of the ladder are not changing. This is an 18-foot ladder. So it's leaning against a building. And this right here is my building. This guy right here is my ladder. Then the base of the ladder starts to slip away from the wall. So what's happening here is that this guy is sliding out this way. Right? The base is sliding away. What happens if the base slides away, because this ladder is a fixed height, if this thing slips away, you have to imagine that then this part has to slide down. In order for it to slip away, it's like it's sliding down. So this part goes down. The top of the ladder against the building is going to slide down. This part is going to slip away. So the base of the ladder starts to slip away from the wall at a rate of 0.75 feet per second. How fast is the ladder sliding down the building when the base of the ladder is 7 feet away from the wall? Okay. So let's talk about what we know and what we want. I honestly might just put this part up here since we have so much room up here. What we know and what we want. All right, well, the ladder is starting to slip away from the wall at a rate of 0.75 feet per second. Okay, well, I need to label stuff then, right? Because I need to be able to label that something is happening down here. This is sliding away. So what I'm going to do is I'm going to label this distance right here as X. You can use whatever letter you want. I like to use the letter X. You can use, D. I would suggest not using D because then you have dd, dt, and that has a lot of D's in it, but whatever you want. So X is going to be the distance from the building to the base of the ladder. And we know that this distance is increasing because the wall, it's slipping away at a rate of 0.5 feet per second, which means that this distance right here is increasing at a rate of 0.5 feet per second. So I get to say that dx dt, the rate of change of that distance from the base of the building to the base of the ladder is 0.75 feet per second. We want to know how fast the ladder is sliding down the building when the base of the ladder is 7 feet away from the wall. So we have to label this distance here because that's, if the ladder is moving down, then this distance is shrinking. Oops. Nope. I just wanted to erase a little bit in there. There we go. So I can label it. I'm going to call this distance y. Y is the distance from the top of the ladder to the floor. So when it says how fast is the ladder sliding down the building, what it's really asking is how fast is this dy dt getting smaller? How fast is y getting smaller? So what is dy dt when the base of the ladder is 7 feet away from the wall? So we want dy dt when base of the ladder, 7 feet from the wall. That would be this distance here. When this distance here is 7 feet. So the quantities we have that we have to relate together are x and y. We have to relate together x and y. So we look at our picture and we think, what in the world could we have that would relate x and y together if we have a picture that looks like this? This is a right triangle. We have a very popular formula here that says that if you have a right triangle, the sum of the squares of the legs is equal to the square of the hypotenuse. It's a squared plus b squared equals c squared. So we get x squared plus y squared equals 324. That's the formula we can use to relate them together. So we're going to take that formula x squared plus y squared equals 324, and we're going to differentiate both sides with respect to time. So remembering, we're not using x like normal. X is a function of time because x is increasing over time. So we need to do chain rule on x and chain rule on y. So we're doing implicit with both of those. So the derivative of x squared would be 2x dx dt plus 2y dy dt. And then the derivative of a constant is 0. Step 4 is plugging things in. So what do we know? Well, we know that dx dt is 0.75 feet per second. We know that x is equal to 7 feet. That should be feet. But that's not going to leave us with enough stuff, right? So I need to fill in dx dt, and I'm trying to find dy dt. But if I fill in x and dx dt, that's going to leave me with a y and a dy dt. So we need to be able to plug in y in order for us to find dy dt. We need everything except dy dt in order to find dy dt. But that's actually not a problem. Actually not a problem. So at this very particular moment in time, and it's very important that we don't do this until we've taken the derivative, we were able to plug in 18 feet for the ladder up here because the ladder does not change. The ladder is always 18 feet long. It does not stretch, it does not shrink. It is an 18-foot long ladder who remains an 18-foot long ladder. So the ladder's length never changes. But x and y do change, so they can't be plugged in until the very end. But here we have an 18-foot ladder. We know that x is 7. We're trying to find y. Well, 7 squared plus y squared equals 18 squared. So y squared is equal to the square root of 18 squared minus 7 squared. And it's not a nice number. So we have y squared is equal to the square root of 275. Oops, that's not right. Not y squared. This is y. So I did 2 steps in one. I moved it over and then I took the square root. So it's not y squared, it's y. Y is equal to the square root of 275, which is not a nice number. It's like 16.58, but we're not going to round yet. So now we're plugging in everything that we know into this equation. So we have 2, and then x is 7. dx dt is 0.75. Plus 2, we know that y is the square root of 275. And then dy dt equals 0. So we have 10.5 or 10.5 plus 2 square root of 275 dy dt equals 0. I'm subtracting 10.5 on both sides. So I have 2 square root of 275 dy dt equals negative 10.5. And then dividing both sides by 2 square root of 275. So we have dy dt equals negative 10.5 over 2 square root of 275. Putting that in my calculator, I get negative 0.32 when I round. This is a distance, and the time units we were given was seconds. And because it's a distance, it's going to be in feet, not feet squared. Feet squared would be an area. Feet cubed is a volume, but feet would be distance. So negative 0.32 feet per second. Now it's time to kind of, so like you might be tempted to be like, all right, dy dt, we found it, good, that's it. You did, but you didn't. All right, so this is negative, and that makes sense because this is shrinking. Y is shrinking. If y is shrinking, your rate should be negative, which is great. However, the question itself asked how fast the ladder is sliding down the building. And if someone's like, how fast are you going? Or how fast is that ladder sliding down the building? You're not going to give a negative answer. That wouldn't make sense, right? In answering the question, it wouldn't make sense to say it's sliding down the wall at negative 0.32 feet per second. That doesn't make sense. So to make it make sense in the context of the question, we would take away the negative because the negative doesn't make sense in the context of this question. Sometimes the negative will make sense, all right? So you can't just always discard negatives. That won't work. But depending on what the question was that was asked, it could be unnecessary. So if it's how fast is the ladder slipping down the wall, the negative doesn't make sense in the answer. So the answer that we would get would be 0.32 feet per second because the context doesn't call for a negative. The ladder is not slipping down at a negative rate. It's that the distance was changing at a negative rate. So what we ended up finding wasn't exactly the same thing as what we were asked. We were asked, how fast does this ladder fall? But what we found was how fast this rate changed, which those are very much related numbers, right? How fast this distance is changing is the same thing as how fast this thing is going down the wall, but one of those is a negative answer and the other one's a positive. Can I answer any questions on this problem? Okay. So ladder problems are a really common one. You see a lot of Pythagorean theorem. You see a lot of Pythagorean theorem type problems in related rates. This next one is another very common type of problem. This is going to be a problem that involves similar triangles. So let's read the problem first. A conical tank with vertex down is 10 feet across the top and 12 feet deep. If water is flowing into the tank at a rate of 10 cubic feet per minute, find the rate of change of the depth of the water when the water is 8 feet deep. So, like I said, reading these problems, there's a lot to take in at once, which is why drawing the picture to help yourself understand what's going on helps. So I start here and I say, a conical tank with vertex down. So vertex is the tip of the cone. So this is a tank that looks like, let's see. It looks like this. But I don't love that picture, so I'm going to redo it. Feels kind of tilty. Okay, here's my tank. We know a few numbers that don't change. I know that the distance across the top is 10 feet. I know that the depth of the tank is 12 feet. I know that there's water flowing into the tank. So, I don't know, maybe there's a hose or something. And it has water that's flowing in. So there's some like water level down here, right? Because there's water in the bottom of the tank. And if you really wanted to, you could label like that this is rushing in at 10 cubic feet per minute if you really wanted to put that there because the water is rushing into the tank. We want to find the change of the depth of the water when the water is 8 feet deep. I'm actually going to need to move. Well, no, I can put my similar triangles down below there. That's fine. So here's my picture. what do we know? So I know that the water is coming into the tank to fill it up with water. Like I have water being poured into the tank and it's filling up. So the volume of this cone is increasing at 10 cubic feet per minute, right? Because the volume of the water is getting bigger at a rate of 10 cubic feet per minute. So the volume of this cone is getting bigger at a rate of 10 cubic feet per minute. What we want to know, find the rate of change of the depth of the water when the water is 8 feet deep. So we need to label the depth of the water. So the depth of the water would be this distance here. I'm going to call that distance h to be like the height of the water. So we want to know the change in the depth of the water, the height of the water, when the water is 8 feet deep. So we want dh dt when the height of the water is 8 feet. Okay, so we want to relate together height and volume of a cone. And the formula we can use the formula of a volume of a cone, right? The volume of a cone is V equals pi over 3 r squared h. This is the volume of a cone. Well, that's fantastic, except we have a tiny bit of a problem here, and that we have r's involved. And r's are a problem here because the radius of a cone is changing. So the cone that we're talking about, the volume of the cone, we're talking about the volume of this little baby cone here. Because the volume that's changing is the volume of this baby cone. The height that's changing is the height of this baby cone. And the radius of this baby cone is changing, but if we were to go ahead and do some derivatives right now, we'd be taking the derivative of r and of h, we'd have to use product rule, and then we'd end up with a dr dt, and we don't have any information on dr dt. So this r right here is a problem to us. We can't just plug in a number for r because the radius does change over time. So we need to find a way to get rid of r without plugging in a number. And here's where the trick comes in. There's a trick here. The trick, my friends, is called similar triangles. So, imagine, if you will, we have a big right triangle here. This is the cone. Right, this big right triangle. And it is 10 feet across the entire top of the cone, so it would be 5 feet across the radius of this if I drew a cross section here. And the height of this tank is 12 feet. So this is the tank. Inside, once again, looking at a cross section, we have a water level. So I'm drawing like this cross section right here. And we already called this distance h. So maybe I'll be very clear with this. This distance is 12 feet. We already called this distance h. We can call this guy right here the radius of the water. We can call him r, right? Because that's the radius of this cone that we want to know the volume for. We're going to use similar triangles here. So with similar triangles, this is an instance of similar triangles. They're basically proportional to one another. So this triangle is proportional to this triangle. Setting it up, you set up the proportional sides. There's a bunch of ways to set up similar triangles, but setting up proportional sides, r is to 5 as h is to 12. So the setup of that is r over 5 equals h over 12. That's from similar triangles. If you need to look up similar triangles and refresh yourself on them, now is a good time to do that. But for similar triangles, that's the setup of the ratio of similar triangles. If we don't want r in here, we can solve for r in terms of h and then plug it in. So if I multiply both sides by 5, I'm going to get that r is equal to 5h over 12. And that's going to get plugged back in for r. So the formula becomes v equals pi over 3, and then instead of r, we have 5h over 12 squared times h. This is all to avoid having r's in our volume. So we can't even take a derivative yet because we have r's in our volume, and we can't have that because we can't take the derivative of r because we'd have dr dt, and we don't have anything to plug in for dr dt. So if you simplify this a bit, you're going to get an h squared and an h, so you're going to get an h cubed. You're going to get 5 squared on top, so you're going to have 25 pi over 12 squared, so 144 times 3, should come out to 432 h cubed. That's our new formula that relates in this particular scenario. So this, let me be very clear. This formula works for this very particular scenario we're in. If you are in a different similar triangle situation, you're going to have different ratios. This formula will not always be a way to relate volume and height, volume of a cone and the height of a cone together. It works in this very particular scenario. Every similar triangle will have a different ratio. But now that we've done all that work, we are good to differentiate. Sorry, I don't know what happened there. So somebody asked, appreciate your husband writing the specific scenario. So this, so every related rates is its own unique problem, I guess is what I'm trying to say. It works in this specific scenario because in every scenario, you have different cone shapes. So if you had a cone that was 20 feet wide on top, it would change the ratios here, which would make it different. So it's not because this is a specific scenario where like, oh, this is unique and there is a real formula you can use to get here. There's no formula that will always work. It's always going to be different depending on the scenario you're in, just to clarify. So depending on the scenario, it'll be different. So now I'm going to differentiate with respect to t. So dt. When you get sick of changing colors, so you just do it all at once. There we go. So the derivative of volume would be dv dt. And then 25 pi over 432, that is just a number, so he'll stay out front. The derivative of h cubed would be 3h squared dh dt. So I'm trying to have everything on the screen here. So we have dv dt, we have an h value. We can write those down. So let's see, dv dt is 10 cubic feet per minute. H was 8 feet. We can plug those in, and we're solving for dh dt. So dv dt is 10, so we'll put 10 here. And then we have 25 pi over 432 times 3, and then h is 8, so we'll have 8 squared dh dt. If you simplify here, and you do 25 pi times 3 times 8 squared divided by 432, you're going to get, I hope, 4,800. Let me just double check and make sure that number's, yeah. So you're going to get 4,800 pi over 432 dh dt. To get dh dt by itself, you're dividing by 4,800 pi over 432 on both sides. Or multiplying by the reciprocal. It's the same thing. So you're going to get the dh dt is equal to 10 times 432 over 4,800 pi. Which should give you 0.28647, so rounding to 2 decimals, 0.289, or sorry, 0.29. So this is approximately 0.29, and then height is a distance. The time we have is minutes, so this should be feet per minute. The height is changing at a rate of feet per minute. And that makes sense. The height is increasing, so it makes sense that this number is positive. And that is the change of depth of the water. The depth is changing at a rate of 0.29 feet per minute. So as you can see, these related rates problems are a lot of problem solving. They're a lot of fun if you allow yourself to have fun with them. But I think that requires taking the pressure off and just doing it in a fun scenario, not in a math setting. If you could just try to think of it as I'm doing a puzzle as opposed to I'm doing math homework. Someone said I try to get away from geometry, but it keeps following me. Geometry will never stop following you. Geometry will be with you for the rest of ever. Similar triangles, all those formulas for volume, surface area, perimeter, area, it will be with you guys forever. I wish I could say it gets better at any point. I mean, I guess if you go and do a math degree, you just stop talking about numbers altogether, and geometry becomes much different. We had one of my favorite classes I took in undergrad. I hated the professor. The professor was awful. But it was a class on knot theory. So that was really fun. So it's geometry in a different way. He talked about knots and surfaces, and that was fun. But geometry, if you go into higher math, it follows you in a different way. And you never fully escape it. Which is exciting because geometry is a lot of fun. All right. All right. So this next problem is going to be a shadow problem. There's a lot of very classic related rates problems. The ladder problem is a very classic problem. The tank problem, very classic problem. This is going to be a shadow problem, and shadow problems, or sometimes known as lamppost problems, are very typical related rates problems. The more related rates problems you do, the more you'll see of the same scenarios being repeated. So that's why practicing is important, because once you've seen enough scenarios, it makes it a lot harder for them to be tricky. All right, so we're going to read the problem. A 7-foot tall basketball player is 20 feet from a lamppost that is 28 feet tall and is walking directly toward it at a rate of 4 feet per second. Determine the rate of change of the length of his shadow. The first time you see one of these, it requires someone telling you how to set it up. After you've seen it set up once, it becomes a lot easier. So let's talk. There's a lamppost. I am not an artist, so this is a lamppost. You are going to appreciate it for what it is. Is lamppost one word? He has it as one word. It doesn't feel like it should be one word. Feels like it's 2 words, but that's fine. Whatever. Lamppost. Cool. I'm assuming that the notion that this is a basketball player was because the person is very tall. So this is a 7-foot tall person. I don't know what the tallest person is, but 7 feet tall seems pretty tall. Anyway, so we have a tall person. I'm going to draw them. Nope, that's too short. Let's come in here and draw them right there. All right, there's my person. Literally, you do not need to be an artist. You just need to be able to draw stick figures and small diagrams. So he is walking towards the lamppost. Cool. Now what? Well, let's see. The basketball player is 7 feet tall, so I can label that he is 7 feet. The lamppost is 28 feet tall, and that's not changing. The basketball player is not changing, and the lamppost isn't changing in height. They are remaining the height that they are. And then there's some notion of a shadow. And the shadow part is the weird part here. So, the way that light works, hypothetically, is it does like this, right? Okay, hypothetically. Let's just, So then, when the light hits the top of this man, it is no more after here, right? The light stops right there. And the shadow that is cast, so if I draw like a line, If I just continue this down, the shadow that is cast is right here. That is the shadow that he has cast. Right? Like I said, this is a problem that you need to see set up the first time. Right? You're not going to get it the first time. I remember the first time I saw one of these problems, I was like, I don't know if I saw it before I'd gone to class or in what scenario, but I was like, I don't even know what's going on here, because you have to have someone show you what pictorially is happening the first time. These shadow problems work in different ways. You can have like crazy scenarios where like the lamppost is retractable and it moves up and down. You can have scenarios where they're walking towards it, walking away from it. Maybe the person is shrinking. There's a bunch of different scenarios, but when it comes down to it, the point is when the light hits the top of the thing, the shadow is cast in the remaining area down below, the projection. Okay, that's cool. We're clearly going to need to label some stuff, but it'll be easier for us to do that once we have labeled what we know and what we want to know. So what do we know? We got the 20, let's see. So a basketball player is 20 feet from a lamppost that is 28 feet tall. I'm going to come back to this 20-foot thing because he doesn't remain 20 feet from the lamppost since he is walking towards it. And he's walking directly towards it at a rate of 4 feet per second. Determine the rate of change of the length of a shadow. So there's clearly, we have to label his shadow, right? We have to label his shadow. I'm going to call his shadow Y, and you'll see why I'm doing that in a second. I'm going to call a different distance X. So his shadow is Y, and we can figure out the change of length of a shadow by finding dy dt. That's in fact what we want. We want dy dt is the rate of change of his shadow. Oh, and somebody's saying something about sorry, I just noticed in the chat. I hated the shadow problems in Algebra 2. I'm glad that you saw shadow problems in Algebra 2. Because they don't always show those shadow problems. But now you'll learn to love them because they're in the context of related rates, which is way more fun. Okay, I think I need to. If you were here earlier today, hold on, I'm gonna pause this first. And we're back. So anyway, the shadow, the rate at which it's changing would be the dy dt, the rate at which y is changing, and y is the length of the shadow. But we have to do something with this 4 feet per second thing. All right, we have to do something with that. So I'm going to label this distance, and I'm going to call it x. I know, because this guy is walking this direction at 4 feet per second, I know that this distance is shrinking at a rate of 4 feet per second. This shrinking part is actually really important. If you said that dx dt was 4 feet per second, that would mean dx dt is getting bigger. Not dx dt, that would mean that x is getting bigger. That would mean he was walking away from the lamp. Because x is shrinking, dx dt needs to be negative. So we know that dx dt is negative 4 feet per second. Da, 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 da. 7-foot player, 28-foot lamppost. 20 feet from a lamppost. All right, so at the moment we're interested in, he is 20 feet away from the lamppost. So we want dy dt when x is 20. Once again, for formulas. This is, and lamppost problems almost always are, similar triangles. Because you got this triangle and you have this triangle. I'm gonna make that bigger. So maybe I'll do this in green. So this is 7 feet. This is y. Right. And to be very clear, y goes from here to here. This is 28 feet. And this distance from here to here is x. Now, for this triangle, you want to look at the two triangles together. Right? For the small one, we have y and 7. For this big one, we have 28 here, but we don't have x here. Right? It's not just x that goes here, because this distance, this entire bottom part, is the two of them together. It's x plus y. Right now we are working on a formula because we are trying to relate together x and y. So for this similar triangle setup, right, x plus y is to y. Those are the corresponding sides. X plus y over y, and then 28 over 7. So it's big triangle on top, right? Big triangle. There's a bunch of ways to set up similar triangles. But in the way I'm using it, big triangle is on top of the fractions, the small triangle is on the bottom, and then it's the corresponding sides. So x plus y corresponds to y, so they're together, and then 28 corresponds to 7, so they're together. And then you can just cross multiply to make it so that there's no more fractions. So you have 7 times x plus y equals 28y. 7x plus 7y equals 28y. And, you know, we could get the y's on one side and the x's on the other. It doesn't matter. You could do it anyway, but it's easy to combine stuff now. So we'll combine and we'll just move the 7y over. So we'll have 7x equals 21y. This is the formula we're going to use. I was trying to make that easier, but I don't think it's going to make it easier to move it. There we go. So step 3, we're going to differentiate. So we have 7x is equal to 21y. Taking the derivative with respect to time on both sides. So the derivative of 7x would be 7 dx dt equals 21 dy dt. Right? And then I look at the stuff I have to plug in. I know dx dt equals -4 feet per second. And I know we want dy dt when x is equal to 20 feet. But here's the interesting thing. There's nowhere to plug x in. And sometimes that just happens. So the information you collect, sometimes you're given extraneous information. Sometimes you're given information that doesn't matter and doesn't get used. He could have been 10 feet away. He could have been 15 feet away. He could have been 2 feet away. That 20 feet away doesn't matter in the context of this problem. And that's just, related rates problems are like that. So plugging in the dx dt, which is the only thing we have to plug in, 7 times -4 is equal to 21 dy dt. Right? Dividing both sides by 21, you're going to get that dy dt is equal to -28 over 21, which is approximately -1.33, and then the units are in feet per second. Now, we should double check the context of this problem to make sure that makes sense. So it's saying determine the rate of change of the length of his shadow. So it makes sense to keep the negative in here because if this was positive, it would mean his shadow was getting bigger, but the negative is important in here because it signifies that the shadow is getting smaller. So his shadow is shrinking at a negative rate because his shadow is getting smaller. So that negative makes sense in the context of this problem. Let's see. Any questions on this one before we get started on the next problem? Somebody said I don't know what it is about these, but they're kind of fun. I agree. I think these are fun. So the thing is, like, if you let yourself not be anxious about it, if you let yourself just kind of look at it like it's kind of like a game, it's a lot more fun. And I think that's why I've always liked math. So the 28 over 7. Can't use some. Do you mean the 28 over 21? Oh, let's see. Like x. Wait, oh, sorry. Oh, right over here is what you're saying. Ah, yeah, totally. You could have done that there, and you could have also divided it here. Yeah, so if you had done that, so if here you weren't just like going through the algebra, if you were like, hey, I'm a little smarter than that, I can do the 4, you could absolutely do that. Then you'd have x plus y equals 4, and then 4y. No, 4y. There's where the y goes. And then you would have x equals 3y. And then you would get dx dt equals 3 dy dt. And you would end up with the same answer. So you would have -4 equals 3 dy dt. And that would give you dy dt. equals negative 4/3, which is negative 1.33. So, yeah, absolutely could have done that. That's what happens when I just kind of go through the steps without questioning it. But absolutely you could have, and it would have made it slightly nicer. No problem. No problem. Other questions on this one? Okay. So I'm going to look at the ones we have remaining because we have like 25 minutes left. So I want to make sure. So let's see. We have this one, which is okay. Let's see. We have this one. And then we have this one. You know, I think I'm going to do this one. I think so. This is problem 2.7.7. I think I'll do this one. Unless he added a one in here. No, he didn't. Okay. Let's do this one. So, a balloon rises at a rate of 3 meters per second from a point 30 meters away from an observer. Find the rate of change of the angle of elevation of the balloon from the observer when the balloon is 25 meters above the ground. Pictures. Okay, we have a person on the ground. There's going to be a balloon that's rising. So this person's on the ground and they're 30 meters away from where this balloon is rising. So this balloon is like, I mean, you know, use your imagination. It's a balloon. And they're on the ground 30 meters away. This balloon is rising, so it's going up. And let's see, so a balloon is rising 30 meters away from the observer. Find the rate of change of the angle of elevation of the balloon from the observer. So the angle of elevation from this observer is this angle right here. This angle is the angle of elevation. So in terms of angle of elevation versus angle of depression, if you are a person, technically it's at eye level, but this angle right here is the angle of elevation. And this angle here, like downward from your viewpoint, this is the angle of depression. Just as a recall from, I don't know, I think you talk about it in math something. I don't know. I think you talk about it at some point, but you might not have seen it for a while. So anyways, the angle of elevation is like the one that goes upward. I'm going to just do it from his feet because we don't know how tall this observer is, and I don't think that's supposed to be part of the problem. So what do we know? We know the balloon is rising at 3 meters per second. So I can label this distance here from the ground to the balloon and call that h, the height difference between the balloon and the ground. So we know that dh dt, that distance, is getting bigger because the balloon is rising. So that's 3 meters per second. We want to find the change of the angle of elevation, so as this thing gets up, that angle of elevation is going to grow, the angle of elevation of the balloon from the observer when the balloon is 25 meters above the ground. So we want d theta dt when h is equal to 25 meters. This requires you digging back into your trigonometry, which is my favorite thing in the world. That is not sarcasm. I love geometry, or not geometry, trigonometry so much. Trigonometry is amazing. Anyways, we have to relate together h and theta. So my ultra simplified triangle here, this is theta, this is h, and we know this side length is 30. It doesn't change, right? He's 30 meters away from that balloon, and that's not changing from the spot on the ground where the balloon began to rise. So using these three things, we have an angle. We have its opposite side, and we have its adjacent side. Which trig function uses opposite and adjacent? Which trig function, which trig ratio uses opposite? There it is, tangent. So Katoa, tangent uses opposite and adjacent. So tangent theta is equal to opposite over adjacent. So we have tan theta is equal to opposite over adjacent. Now, just to avoid having fractions, we can multiply both sides by 30 just to get 30 tan theta equals h. So we have 30 tan theta equals h, and we're going to take the derivative with respect to time. For tangent theta, so the derivative of tangent is secant squared theta, but then we have to put in the d theta dt to account for chain rule, and the derivative of h would be dh dt. So plugging in what we know, we know that dh dt is 3 meters per second, and we know that h is 25. But that's kind of a problem. We want d theta dt. We want d theta dt. We don't even use h. We have dh dt, but we need to know what theta is because we don't have enough information to plug theta in. So we need theta when h is 25. The pro tip is we can use this formula here. So h is 25, so we have tan theta is equal to 25 over 30, which if you really want to reduce that, you can reduce that down to 5/6. Then to get theta by itself, you take the inverse on both sides. So essentially, tan inverse on both sides, these tangents cancel. And you get theta equals tan inverse of 5/6. So we have that information now. Plugging in everything we have 30 secant squared, and we're going to have to be really careful with, I'm going to do parentheses. Secant squared theta is tan inverse of 5/6 times d theta dt equals dh dt is 3. So solving for d theta dt, you'll get 3 over 30 secant squared of tan inverse of 5/6. Now we need to round this, and this is going to require a little bit of being tricky here. All right. Because one thing, your calculator doesn't have a secant button. All right. You have no secant button on your calculator. That does not exist. So first things first, make sure your calculator is in radian mode. Theta should always be in radians and related rates problems. This is very important. It has to do with radians being a unitless angle, whereas degrees have units. But it's important that everything is in radians. So make sure your calculator is in radian mode. Then, secant is partners in crime with cosine. So a secant in the denominator is the same thing as a cosine in the numerator. That is to say, if you have 1 over, let's just say, if you have 3 over 30 secant squared of theta, this is the same thing as 3 cosine squared theta over 30. So secant in the denominator is the same thing as cosine in the numerator. So this is 3 over 30, not 3 over 30, hold on. 3 cosine squared of tan inverse of 5/6 over 30. Now you have a cosine button, but when you enter it, you're going to want to enter it like this, because this is important. If you have the Casio calculator, the fraction part's no problem. But you're going to want to put parentheses, cosine, tan inverse. There is a button for tan inverse. It should be right above your tangent button. You might have to use the shift key to get to it. Let's see, close, and square it like that. Because you can't put the squared right after this in your calculator. And then divide by 30. So if you do that, sorry, hold on just a second. Going now, plugging this into your calculator. And you do want to practice this. You should get rounding to 2 decimal places, 0.06. And then because we're talking about the change in theta is in radians, so it's radians per second. Technically, radians are a unitless angle, but like you would say radians per second. And that would be your answer. So remembering your trigonometry is important here. You can do things like you could do tan inverse of 5, 6 on your calculator, but you need to make sure you take lots of decimals with it. So if you do this, if you just do tan inverse first, take at least 4 decimals with you, because if you only take 2 decimals, there's chances that rounding errors can happen. So if you're going to do this in steps, every step you should take 4 decimals with you. That avoids most rounding errors. So with the 10 minutes we have left, I don't really have time to go through another example, and I don't want to start something I can't finish. But are there any questions on anything right now that I can answer? Remembering that we do have the optional review session that will be on Friday, which will be recorded and posted. If not, then I will remind you once again to please make sure you look at the Exam 2 review. Now that I have a big chunk of grading from one class out of the way, I'm hoping to get a head start on the homeworks. So grading the homeworks and the exam makeups. I'm hoping to get a head start on that today, but I need to stand for a little bit and stretch for a little bit. But all right, well, if there's no questions, then that'll be it for today. I'll let you go like 9 minutes early. Enjoy those 9 minutes. Maybe go meditate or take a walk, sip some tea, do something good with those extra 9 minutes. I'll stay if there's any questions, but other than that, have a fantastic weekend, or I'll see you on Friday, in which case have a fantastic Wednesday and Thursday.